Hi everyone. Today, Ishan, Parth, and I will be talking about how the usage of specific filters during the image reconstruction process of filtered back projection changes the characteristics of background noise in CT images. So, to begin with, let me try to explain the goals for our presentation today. Firstly, we are going to analyze four datasets through filtered back projection. Three of them are going to be with different distributions of circles, and one would be a clinical lung CT scan. We would then next try different specific filters and use varying noises for each dataset individually, and finally compare the results for sensitivity and specificity of reconstruction during filtered back projection. So just to give you a basic summary on filtered back projection. Filtered back projection is a fast and direct method to generate CT images. It consists of two main steps, filtering the data and performing the back projection operation. Just stepping back a little, back projection refers to the process of running back projections through an image to reconstruct itself. So during this process, certain other areas of the image tend to get blurry. And to avoid this, a high pass filter is used in the process. And this entire phenomenon or process altogether is referred to as filtered back projection. As you can see in the examples provided, a final image through filtered back projection is much more precise and clear as compared to the one with unfiltered back projection. So moving over, some of the high-pass filters we would be using during our FPP would be some of the common ones known, the ramp, Shep, Logan, cosine, Hamming, and the hand filter. The ramp filter is a standard or default filter, which is used in most cases, whereas the other ones mentioned here are the ramp filter multiplied by either a sync, cosine, Hamming, or a hand window. All these filters would be used in our assessments for the project. So for our project, we would be using a total of four datasets. The first three would be pictures of differently organized circular projections in an image, whereas the last one would be a clinical lung CT scan, which is probably infected with an infection. Now passing over the presentation to Parth, who would be getting into more detail about our methods and further analysis.
Okay, so I'm going to talk a little bit about our method and the data that we use for this method and the outputs of this method. Um, so basically, the aim of our little experiment here is to see how different filters affect back projection of noisy images. And we quantify this using the sensitivity and specificity um, of a detection of certain artifacts given some detection model, right? So we have an original image here. This is just a sample image. Uh, and this image is meant to simulate a real CT image with some artifacts or some points of interest. So each circle here is a point of interest. And maybe in a real CT image, you would have some sort of cancerous nodules that are, circular or close to circular in shape. And maybe you have a radiologist who actually identifies these points of interest, or you have some sort of model which can detect these points of interest. Or maybe that's like a deep learning model. For our purposes, we use a simple circle detection model. Um, and that serves as our detection model to identify points of interest. So what we do is initially we run this detection model on the original image, right? And we get these ground truth points of interest. So every circle highlighted in light blue or cyan um, is identified by our detector or our algorithm or our model. And these interest points now become our ground truth interest points. What we want to see is, in case you were to add some noise to this image, or you had a noisy process of reconstructing uh, the image, and if you reconstructed this image using back projection with a particular filter, let's say the RAM filter or the Hamming filter, and you ran that reconstructed filter back through this model, what would be the performance of detection of the same model on a reconstructed image using some filter, right? So to simulate that, we add some noise to the image of the order of 1% to 10 or 20% in increments, and we have a noisy image here. Um, we take the radon transform to get the sinogram, and then we back project this with different filters. And we pass the back projected image again through the same circle detection model. And finally, we get to the detected interest points on the back projected filtered image. So this is an example of interest points. The interest point is detected on the back projected filtered image, shown in pink. And then we compare these to the interest points on the original image, and we get a sensitivity and specificity of detection. This is what we use to quantify the performance of the filter. So broadly, this is our method, and this is meant to simulate a real world situation where uh, you have some CT image, you have certain artifacts in that. You reconstruct that CT image from the sinogram. using, let's say, a RAM filter or a Hamming filter, and you want to see what effect that filter has on certain interest points in your image, given that your image or your imaging process has some noise. So each filter is going to affect these interest points and noise differently, and you want to quantify this. And the clever thing that we have done here is by taking like a fixed image with simple circular artifacts, we actually have um, a ground truth set of interest points against which we can compare the performance of each filter and actually quantify the performance of each filter, which would not be possible probably in a real world setting.
Hi, good morning everyone. My name is Ishan Gupta and I'll be proceeding forward with the next part of this presentation. So now we'll be talking about the sensitivity and the specificity analysis on different types of sample images. So you see the first sample image we have is that of circles with different sizes, right? So we introduce white noise to this image, reconstructed it back using inverse rate reconstruction and pass the image to different types of filters, for example the RAM filter and the Hamming filter. So you can see that after that, the image was passed to the circle detection algorithm, and we can see that a lot of false positives have been detected with the RAM filtered image, whereas a very few of them are those available in the Hamming filtered image. So these results are pretty much evident in the plots that we have shown below. So they talk about the specificity and the sensitivity at different noise levels with different types of filters. So we can see that with RAM filter, the specificity drops down drastically as the noise levels are increased, whereas with that of Hamming filter, it's pretty much constant. And the reason behind this is that that specificity is basically the measure of the true negatives. So in our case, the uncircled region getting truly undetected is basically the measure of the specificity. But in our case, when we talk about the RAM filter, we see that a lot of false positives have been introduced or detected wrongly, right? So that is because RAM filter introduces a lot of noise, which is incorrectly detected as circles by the algorithm. That's why the specificity is pretty low with the RAM filter. Now, if we talk about the sensitivity, we can see that with the RAM filter, the sensitivity levels are pretty high at higher noise levels. So this is because the RAM filter introduces a lot of high frequency components, which basically makes the edges very sharp. And those sharp edged circles are having high resolution and are easily detected by the circle detection algorithm as compared to the Hamming filter. Now moving forward to the next sample image, we can see that here we have circles of pretty much the same size, but they're not true circles. They're kind of distorted circles, right? And doing the same analysis on this image, we can see that the specificity and the sensitivity trends are pretty much the same. But if we look closely at the sensitivity plots, you can see that the overall generic values for all the types of filters for sensitivity is pretty high in this case as compared to this case. Because here the sensitivity levels are around zero point 0.6, 0.62, whereas here, the sensitivity levels are around zero point 0.8 for RAM filters at low noise. So the reason behind this is that here we can see that the circle sizes are high as compared to the circles which are very small in this image. And you can see that a lot of them are undetected. So they are basically the false negatives, right? So because the false negatives are pretty low in this image, whereas they are pretty high in the previous image, we can see that the sensitivity values are pretty high generally in this kind of image. So we can conclude that the small circles are not very well detected with any type of filter. Now moving forward to the last CT scan image, we can see that here the lesions in the lungs are basically the circular nodules. So we did the same analysis and we passed the image reconstructed one to the ramp and the Hamming filter. And we can see that the similar trend has been observed with the specificity and the sensitivity analysis. But overall, if you look at the sensitivity plots, you can see that with all the filters, the sensitivity levels are pretty low. So this brings us to the conclusion that the RAM filter helps to detect sharp edges better as compared to Hamming filter, whereas the Hamming filter introduces less noise than the RAM filter. Also, the RAM filter provides better sensitivity at higher noise levels, whereas the Hamming filter provides better specificity at higher noise levels. Now, if we compare the filters based on circle size, we see that the specificity trend is about the same for both large and small circles, whereas the sensitivity is generally higher for circles with larger sizes as compared to the ones with smaller circles. There are certain drawbacks that we observed with our project. So we see that the sensitivity of all filters are pretty low for lung CT scan with small size lesions. That is probably because the circle detection algorithm doesn't work very well with small size lesions as they're not always circular. And further, maybe all the different types of filters, they were not able to resolve the smaller circles very well so that they can be easily detected by the circle detection algorithm. So certain future prospects are that we can probably use convolution neural networks to train and classify the lung CT images and detect whether they're cancerous or not. So that is pretty much from my side. These are certain references. Thank you. Thank you so much.